In this video, we'll be doing more examples from section 3, which is entitled Combinations, but not all of these problems will be combination problems. Some of these will be fundamental counting principles, some of them can be done by permutations. The author has a selection of problems from 41 through 60 where he mixes those kinds of problems together. And so I thought it would be good to go through these so we can talk about why we use the method we do on a particular problem, how you determine which is appropriate. First example I'd like to demonstrate is on page 301, problem number 41. It says, in a race in which 6 automobiles are entered and there are no ties, in how many ways can the first 4 finishers come in? Okay, so we're trying to decide between our 3 methods of combination, permutation, and fundamental counting principle. And since this is a race and we're paying attention to the order, the first 4, the order in which they come in, that means combinations are out. In a combination, order does not matter. So we're down to permutations and fundamental counting principle. And when I have both of those as options, I like to draw the blanks because any problem that can be done by a permutation can also be done by fundamental counting. So the safe play is to draw the blanks. And then if I notice that it's a permutation problem after I set it up, then I might put it into the calculator that way. So in this race, there are 6 cars, and any one of those 6 cars could come in first. So there are 6 possible cars for the first spot. But once that car has finished, then there are only 5 cars remaining. So there are 5 cars left over for second place. And when those 2 cars have gone across the finish line, that leaves 4 cars for third place. And after those 3 cars have finished, that leaves 3 cars for fourth place. And the fundamental counting principle says we can just multiply those numbers together. 6 times 5 is 30. 30 times 4 is 120. 120 times 3 is 360. And there are 360 ways that the first 4 finishers could cross the finish line. However, some of you might have noticed that in this example we're choosing and permuting 4 distinct elements. And so this is also 6p4. And I'll show you in the calculator that it gives you the same thing. To do 6p4 in the calculator, you're going to type the 6 key, push the math button, scroll to the probability heading. This is a permutation because order matters, so choice 2. There are 4 cars that we're going to choose and then order. And 6p4 really is 360. Either way would work. The next problem is problem 43 on page 302. A medical researcher needs 6 people to test the effectiveness of an experimental drug. If 13 people have volunteered for the test, in how many ways can 6 people be selected? Notice that they're not putting the people in any specific buckets. They don't have special roles in the test. They're just choosing 6 people. And so the order in which those 6 people are selected does not matter, and that makes this a combination. So there are 13 total people to choose from, and we need to choose 6. So that's 13C6. Let's run to the calculator with that. I'm going to type 13, then the math button, scroll to probability. Combinations are choice 3, NCR, and we're choosing 6 individuals. And so there are 1,716 different ways to choose those 6 people from the group of 13. Again, the order did not matter, so that was a combination. 45. From a club of 20 people, in how many ways can a group of 3 members be selected to attend a conference? Okay, we're warmed up now. We've had a couple of problems. So I want you to pause the video and think about how you would do this, and then I'll tell you how I would do it. Okay, because they're selecting 3 people just to attend a conference, they're not putting them in specific positions or roles. They're just selecting a group of 3 people. The order doesn't matter, and so this is another combination. There are 20 total people to choose from. We're going to choose 3, so that's 20C3. Run to the calculator. 20, math, scroll to probability, 3, 3, enter. 1,140 groups of 3 people who could be selected to attend the conference. That's a combination because the order doesn't matter. Number 49. Using 15 flavors of ice cream, how many cones with 3 different flavors can you create if it is important to you which flavor goes on the top, middle, and bottom? So you'll notice that they're imposing an order here. I want you to think about how you might do this one. You actually have two options here. Because we're using different flavors in each spot, this is a permutation. But I would do this with the blanks. I would say I'm going to make a blank for the number of choices I have to go on the top, for the number of choices I have to go on the middle, and then the number on the bottom. There are 15 different flavors, and so I could pick any of those 15 for the top. And we've specified that we're going to pick 3 different flavors, which is why you could do this by a permutation. But with 3 different flavors, that only leaves 14 for the middle. And then because we've used those 2 flavors up, that leaves 13 for the third spot. So it's 15 times 14 times 13, which I can't do. So 15 times 14 times 13. That's 2,730. Again, this is a permutation because we're choosing and arranging in an order 3 different objects from a set of 15 objects. So we could do 15p3. I'll show you that gives you the same answer. 15, math, scroll to probability, choice 2 because it's permutation, 3, same thing, 2,730. If there was not this restriction of 3 different flavors and we could in fact reuse flavors, then permutations would not be an option because in a permutation you have to have distinct objects, so you can't use the same object twice. But we could still use the blanks. We would have just had 3 15s, 15 cubed would have been our answer. Problem 51. A restaurant lunch special allows the customer to choose 2 vegetables from this list: okra, corn, peas, carrots, and squash. So notice that's 5 options there. How many different outcomes are possible if the customer chooses 2 different vegetables? Think about that one. Does it matter what order you choose your vegetables in? No, you have the same thing. If you choose corn and peas, you get the same 2 vegetables as if you chose peas and corn. And when order doesn't matter, that's a combination. This is 5C2. I'm pretty sure we've calculated 5C2 in class before. That's 10. But let's just run to the calculator and make sure. 5, math, scroll to probability, choice 3, because it's a combination, 2, and yeah, that's 10. This one's short enough that if you were completely stuck, you could just make a list of all of the different ways to pair 2 different vegetables together. If they hadn't said it was 2 different vegetables, then we wouldn't have been able to do a combination, but that question wouldn't really be fair for our class because you can't do it by permutations or fundamental counting either. 53. You have 3 dress shirts, 2 ties, and 2 jackets. You need to select a dress shirt, a tie, and a jacket for work today. How many different outcomes are possible, which is a weird way of saying how many different outfits could you get. Think about that one. When you ask the question, does order matter? It doesn't really matter what order you select these in, but this isn't an order or non-order question. This is a fundamental counting principle question because you're making 3 different choices. And the number of options you have for each choice gets multiplied together. So this is a little bit different. These aren't all in the same bucket. It's not like you have 7 pieces of clothing and you're going to choose 3 of them without regard to order, because then you could wind up with 2 dress shirts and a tie and not have a jacket. Or even weirder, you could have 2 jackets and a tie with no shirt, which would be horrifying. You're choosing 1 from each bucket, and that's fundamental counting. You're going to choose 1 of the 3 dress shirts. You're going to choose 1 of the 2 ties, and you're going to choose 1 of the 2 jackets and multiply those together. That's 12 different outfits. This one cannot be done strictly by a single permutation or combination. This one's fundamental counting. One more. I've reworded this one a little bit because he has a typo in the book and he's thrown in some extra wording that I thought was confusing. He also left something out of the problem. So I've reworded this one a little bit. It says there are 4 Democrats and 5 Republicans on the county commission. From among their group, they will choose a committee of 2 Democrats and 2 Republicans, and he explains why, but I've skipped that part. How many 4-person groups of this type are possible? In the book, he says how many 4-person groups are possible, but of course he means how many different 4-person groups with these 2 restrictions are possible. So, just like in the last problem, we have 2 different choices to make. We have to choose Democrats and we have to choose Republicans. So for the Democrats, there are 4 choices, and we're going to select 2 of them. And for the Republicans, there are 5 choices, and we're going to select 2 of them. So if we're going to figure out what each of those are, and then use fundamental counting to multiply them together. So 5 choose 2 we just did is 10, and 4 choose 2 I'll show you is 6. So I go to the calculator with this. 4, math, scroll to probability, combination, because the order in which we select people for a committee doesn't matter. And that really is 6. 6 times 10 is 60. And so there are 60 possible committees that have 2 Democrats and 2 Republicans. These are the hardest kinds of problems where you have to fill in the blanks of the fundamental counting principle with combinations or permutations. There aren't a whole lot of them in the book, so if those make you nervous, you could just practice them all, make sure that you've got them down by sending me your answers, and then I can't surprise you with anything on the exam. I really think this selection of problems from 41 through 60 is a good way to practice for the test. I'm pretty sure I skipped a few of them in the recommended problems, so make sure you're paying attention to the recommended problems and only do the ones that I listed. But I like this as an overall review of the first 3 sections of the book. If you have any questions, come to one of my online office hours or see me in a Zoom session for faculty tutoring. If you can't do either of those, email still works. You can just email me your questions.